previously we have learned about the Cramer rule. So for the Cramer rule, we have learned that for using determinant to get the value of x1 and also x2, if we use this particular metric notation x2, the equation to get x2 would be a11, a21, a31, b1, b2, and b3. So you notice that the value of the coefficient is actually corresponding to the x value. So the first, if we wanted to find the value of x1, therefore the coefficient will be situated in the first column, while if we wanted to find the x2, the x equals n equals to 2, therefore we are going to put the coefficient in the second column. And if we wanted to find x3, therefore we are going to get to put the coefficient in the third column. So this is x3, a11, a21, a31, a12, a22, a32, and b1, b2, b3 in the third column, divided by the determinant. So this would be the Cramer rule. The next method that we are going to learn would be the elimination of unknowns. So this method can be illustrated for a set of two equations. So this one we denote as or represent as equation 1, and this as equation 2. So the first step would be to multiply the constant, the equation by constant, so that one of the unknowns will be eliminated when the two equations are combined. So this would be the first step, and the second step would be the result is a single equation that can be solved for the remaining unknowns. So, and that follow with the third step, where the third step, this value can then be substituted into either the original equation to compute the other variables. So for example, if we have 1 and 2 here, therefore we're going to multiply 1 by a21, so here the coefficient here, and we will get this equation x1 plus a12 a21 x2 equals to b1 a21. So this we represent as equation 3. And then for the second equation, we are going to multiply it by a11 to get a21 a11 x1 plus a22 a11 x2 equals to b2 a11. So this we represent as equation 4. So we are going to subtract equation 3 from 4, and we will get this equation 2 minus a12 a21 x. So this part here will cancel out, 21 x2. So this, equals to b2 a11 A11 minus B1 A21. And then we're going to get the value of x2 as, so we solve for x2 to get B2 A11 minus B1 A21 divided by A22 A11 minus A12 A21. So this one would be we represent as equation 5. So later we are going to substitute equation 5 into 1 to get x1 x. So if you try to do it your own, you will get this equation A11 B22 minus A12 A21. So this is equation 6. So if we try to do this for the previous example, we will actually get a similar answer. So for example 3, if let's say that we have these two similar equations to the previous example, and then we wanted to solve for x1 and also x2. So first, if we remember from equation 5 and 6 that we have derived previously, so from 5 and 6 that we have derived, so we will get equation x, the value of x1 as 218 minus 2 times 2 divided by 3 times 2 minus 2 negative 1, and we will get around 4. And for x2, it would be similarly from equation 6, we will just substitute the value of the element and we will get 3. So this is actually the same answers that we get with example 1 and also example 2. Now, for the next method that we are going to learn would be the naive Gauss elimination. So the previous elimination of unknowns technique can also be extended to a large sets of equations using algorithms to eliminate unknowns and also to back substitute. So one of the methods that we are going to use would be Gauss elimination. Although this technique is ideal for computer usage, we need to modify it so that it can be avoid division by 0. However, for the basic method of Gauss elimination, we are going to start with naive Gauss elimination. So why do we call it naive Gauss? So naive Gauss elimination, the word naive here, it does not avoid the issue of avoiding division by 0. So by using naive Gauss elimination, we can actually encounter the problem of the issue where we can divide a certain set of equation by 0. So it consists of two phases. The first one is forward elimination of unknowns, and the second phase would be the back substitution. So this would be, all of this would be the description of the method. So for example, if we have a general set of equation of A11 x1 plus A12 x2 plus A13 x3 plus dot dot dot, and A1. You might ask, what does A11 means? It's actually correspond to the metric notation that we have learned in the previous class. So I hope that you refer back to the video for that particular lecture. So 21 x1 plus. So let's say that we are given this set of equation. So you might need to refer to the previous video. Xn equals to b2. So this is the second equation, and up until, for example, if we have n number of equation, so we're going to have xn x2 plus a n3 x3 plus dot dot dot, and n xn equals to bn. So this would be the third. So along the way we have several set of equation. Now for the first phase, the aim for this particular method would be to reduce the set of equation so that it will form an upper triangular system. So this would be an upper triangular system. So as you can see that we're going to have something like this. This what we meant by an upper triangular system. So here, for example, x1, x2, x3, x2, x3, and this is correspond to x3. So the initial step is to eliminate the first unknown x1 from 2 through the n equation. So previously, if you refer to this general set of equation, you will see that the first thing that we need to do is to eliminate the first unknown x1 from 2 to the nth equation, which is in this case is 3. So the first thing that we need to do is to multiply number 1 with A21 over A11. So how are we going to eliminate this particular value? Is by multiplying. First, we are going to multiply, because we are going to back substitute and subtract it with 1. So we need to make sure the coefficient in 1 for x1 can be cancelled out. So multiply 1 by A21 divided by A11. The reason is that we wanted to get the value of A21 for x1 here for the first set of equation. So by doing that, we are going to get by doing that, we're going to get A21 x1 plus A21 over A11, A12 x2, and A21 over A11, A13 x3, A21 plus A21 over A11, A1n xn, A21 over A11 b1. So this would be, we denote as equation 4. So after that, we are going to subtract equation 4 from equation 2 to get. So if you refer back to the equation 2 that we have stated in this slide, on slide number 19, we will get the value. If you try to do it, I'm going to show you one by one. So if we try to write everything down first, x2 So you will see that for the first several terms here, we are going to see that these terms here cancel out each other to leave us with with the coefficient of x2 and also x3. And we can see that from this equation, this particular result, we can actually see that this is correspond to a prime, the 2 x2 plus plus a prime 2n xn equals to b prime 2. So the symbol prime here indicates that the elements have been changed from the original values. So if we try to repeat it for the remaining equations, so for example, multiply equation 1 by a31 over a11, so that we can subtract the result from the third equation, and subtract from equation number 3, we will actually get the result of a11 x1 plus a12 x2 plus a13 x3. So the first equation doesn't really change much, b1, so we denote as equation 5, and this one a prime 2 x2 x3 plus dot dot dot. So this. Six and a prime 32 x2 plus a prime 33 x3 plus. So this is a, and x n equals to b prime 3. So this equation 7, and if we try to continue it until the nth equation, we will get this. So this is prime n 3 x3 plus dot 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 plus a prime n x n equals to b prime n. So this is equation 8. So if you refer back to the original set of equation, you will see that equation 1 is actually the pivot equation. So the pivot equation is where we are going to base our calculation or procedures, and A11, which is the element, the first element in equation 1, is called as the pivot equation or element. So notice that if we multiply the first row by A21 over A11, so let's say that we multiply 1 by A21 and also multiply A21 over A11, it's also equivalent if we try to divide it by A11 and multiply it by A21. And if we try to repeat the second step, where this step here, we going to eliminate the second unknown from 7. So this is the second unknowns, this one x2. So x2, if we wanted to eliminate the second unknowns from equation equation 7, so if we wanted, because we wanted to have an upper triangular system, therefore we need to eliminate this part here. So if we try to repeat the previous procedure to eliminate the second unknowns from 7 through 8, we can try to do that by multiplying 6 by A. So we can do that by multiplying equation 6 by A prime 32 over A prime 22. Okay, so and then we're going to subtract it, the results. So if we from and subtract it from 7. So if you try to do that, we will yield a new set of equation where it's actually it's similar. It will shown as it satisfy the requirement of upper triangle system. So we will get actually something like this. So the first row here doesn't really change at all. The second row, we're going to have a prime x2 plus a prime 23 x3 plus dot 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 plus a prime 2n xn equals to b prime 2. And for the third equation, you will see that we starting to have a double prime, where double prime represent the element that have been modified twice. So we have double prime here, double prime 3, and so on. If we have n number of equation, we will try to do it until the nth equation. And if we try to continue the procedures using remaining pivot equation, we will get the final procedures is to use the n. So we are going to use the n minus 1 equation, for example 7, equation number 7, to eliminate the n minus 1 term from the n equation, from equation number 8. So at the end, we are going to have something like an upper triangular system. So at the end, we can get the value or the value of this part here. So for example, a double prime 3 3 x is equals to c double prime 3. So we actually can solve for x3. So x3 is actually c double prime 3 over a double prime 3 3. So after that, we can back substitute this equation into the second and the first equation. I know that it's a bit hard for you to comprehend, but for example, if let's say that we have this, so first thing first, okay. So if let's say that we have this particular set, 3 sets of equation, and we wanted to solve the value of x1, x2, and x3, and we're going to keep it to 6 significant digits. So this we represent as equation 1, equation 2, and equation 3. So we're going to have 6 significant digits. So first, what we are going to do is to multiply equation 1 by 0.1 over the pivot element, which is 3, and subtract it from 2. So first we are going to get 0.1x1 minus 0.003333. Sorry, I just remember that we need to keep it to 6 significant digits. So this is x. Is it 3? Let me see. Yeah. So we denote this as equation 4, and then we're going to subtract equation 4 from 2, and we will get this. This is for the first equation, and then we are going to multiply equation equation 1, still equation 1, which is the pivot element, the pivot equation, by 0.3 over 3 and subtract it from 3, equation 3. So the first one we get 0.30000 x1 plus 0.010000, because this is a 6 significant digit, 0.020000, x3 equals to 0.785000. So this is equation 6. Then we are going to subtract equation 6 from equation 3 to get 0.190000 x2, because it's cancel out, x1 cancel out, leaving us with x2 and also x3. So this equation 7, and then we actually get, if we try to list this down, we will actually get this. We will actually get a new set of equation, and from there we can back substitute into the equation. So I will try to show it in the new slide here. So if we try to do this, we will see, so this corresponds to equation number 1. So this is equation number 1, and we're going to see x2 minus 0.293333 x3, negative 19.5617. So this is equation 5 that we have learned, we have derived previously. x2 plus 10 0 x3 equals to 70.6150. So this corresponds to equation 7. So as you can see, this is not a upper triangular system, because we still have this equation. In order for us to have a complete triangular upper triangle system, we need to eliminate this particular element. So first, what we need to do is to multiply 5 by negative 0.190000 over 7.00333 and subtract the result from 7. So first we're going to get 0.190000 x2 plus 0.007958 x3 and this is we represent it as equation 8, and from there 7 minus equation 7, we subtract from equation 7 to get x3 equals to 70.084282. So this is equation number 9. So here you can see that we all actually already solve for x3, can solve for x3. So x3 is actually 0, 0, 0, 0, 3. So this is equation 10. And then we can actually substitute x3 into equation 5 to get x2. If you try to substitute everything, x2, you will get x2 as negative 2.4999. And you can substitute equation x2 and also x3 into 1 to get x1 equals to 3.16667. Or I might have done a little bit of mistake here, but it should be nearly to 3. Right, so from there we can compare it with the previous result, the previous example, where if you refer back to the previous example, the answer for x1 would be 7, x2 x1 would be 3, x2 would be negative 2.5, and x3 as 7. So it's a bit similar to what we should obtain. So from there we actually can get pitfalls of elimination method. So if you refer back to our example that we have done previously, the first thing that I would like to highlight it here would be the round-off error. So this error is actually depends on the significant figure that we use. So previously we only used up until 6 significant figures. So at the end we actually have problem with round-off errors as shown in the previous example. And another one would be division by 0. So if you refer back to the method that we have used, we actually use the pivot element to divide the value of the coefficient of that particular equation. So the problem, there will be a problem if the pivot element is equals to 0, where there will be a case where there will be cases of division by 0. So at the end, the value that we get will not be the correct one. So the third pitfalls would be the ill-conditioned system. So remember, if you remember from the previous slide, we have cases or condition where we have similar equation with the in parallel with similar slope and so on. So if we have this system, it would be very hard for us to use the elimination method. Similarly with singular system. So singular system, if we have two lines that's perfectly the same with each other, and also another one would be the condition where we have nearly singular line. So here for these systems we're going to have problems for elimination method. Number 4, singular system are a bit similar to what we have discussed previously. If let's say two equations are identical, we would lose 1 degree of freedom and be dealing with impossible case of n-1 equation. So it actually not really recommended to use elimination method if we have a singular system. So in order for us to improve solutions, there are several techniques. The first one is to use more significant figures. We actually can format the significant figures that we want in MATLAB, and this is up to us to whether to use a long formatting or a short formatting number of significant figures. The second technique would be pivoting. If the pivot element is 0, so we can actually normalize steep leads that to division by 0. So the same problem may arise when the pivot element is close to 0. So it can be avoided by partially pivoting. So we switch the rows so that the largest element is the pivot element. So for example, if we have x2 plus x3 x3 equals to 13, and for x1 plus x2 plus 5 x3 equals to 1. So this is just an example. I just put random numbers here. So as you can see, we are going to use the largest element as the pivot element, since this one is 0. Here the pivot element here is 0. Therefore, in order for us to avoid the pivot, the pivoting, the problem of division by 0, so what we can do is to interchange these two rows. So this one will be going up and this row going down. So in a way, it will change the pivot element to 5. And also another one would be complete pivoting. So searching for the last element in all rows and column, and then we switch it. So this is a bit similar to this. The only difference would be partial pivoting would be similar to complete pivoting if we have quite a small number of equation. If it's a big number of equation, then we're going to have complete pivoting, where we're going to search for the largest elements in all rows and column, then we switch it all together. So we're not going to do this in this course because it's quite complicated for you to comprehend, but it's good for you to know about this. And another thing that another method that you will not be using but still need to know would be the Gauss-Jordan elimination method. So we are not going to focus on this method because it's quite complicated. Therefore, I'm going to just brief you a little bit on it. It's actually a variation of Gauss elimination, where the major differences are actually when an unknown is eliminated, it is eliminated from all equation rather just the subsequent ones. So for example, if we have equation 1, equation 2, equation 3, actually previously we just do it one by one. So let's say that we wanted to eliminate x1 from equation 2 and equation 3. We only eliminate from this part. Actually, if we use the Gauss-Jordan elimination method, it will eliminate it from all other equation. For example, even the equation that on top of it. So all rows are normalized by dividing them by their pivot element. So this is a bit similar with the knife Gauss, but in knife Gauss, we are normalizing or dividing it by different value. So for example, for row 2 we have different value of pivot element, and then for row number 3 we have different pivot elements and so on. However, for Gauss-Jordan we are going to divide it by their pivot elements, and then the elimination step result in identity matrix, if you remember, and consequently it is necessary to employ back substitution to obtain solution. So this is a bit complicated for us to comprehend for this particular course due to lack of time. Therefore, I just wanted to emphasize here that instead, in addition to knife Gauss elimination, we also have Gauss-Jordan elimination. However, we're not going to do this technique here in our course, in this course. So I think that's it for today. I'm going to meet you again during the tutorial on Friday. Thank you very much.